Okay, introduction to the course on advanced machining processes. Today we are going to discuss on a new type of advanced machining process, which is mechanical type of advanced machining process, that is called abrasive jet machining process. So this is the organization of my lecture. So first we shall discuss, we shall introduce the process, and then I shall discuss that what is the working principle of advanced this abrasive jet machining process. Then I shall discuss that experimental setup of abrasive jet machining, what are the different components of abrasive jet machining process. Then we shall discuss some mathematical modelings for calculating MRR, material removal rate, in abrasive jet machining process. Then we shall discuss the parametric analysis. There are different parameters are there which governs the process. Okay, so what are the effects of different parameters on the material removal rate, accuracy, and different other things, so suppose surface toughness. Then we shall discuss about the process capabilities. What are the things we can do? What are the different applications of this abrasive jet machining process? And after that we shall discuss some solved examples. Okay, so we shall take some examples and we shall discuss how to solve different kind of examples. Okay, so now introduction to the process. Okay, so this is the mechanical type advanced machining process. This abrasive jet machining. So it is a mechanical type of advanced machining process. So other mechanical type of advanced machining process are abrasive jet machining, then ultrasonic machining, then water jet machining process, then abrasive water jet machining process. Okay. So there are different finishing processes also, mechanical type finishing processes also. Okay, so these are basically narrow finishing process. So these finishing processes are abrasive flow finishing process or AFM process, magnetic abrasive finishing process or MAF process, chemomechanical polishing process or CMP process, magnetorheological finishing process or better known as MRF process, and magnetic float polishing process. It is known as MFP, magnetic float polishing process or magnetic float finishing process, and this process is used for polishing balls, which is used in bearings. Okay, so these are the different kinds of machining process, mechanical type of machining process, advanced machining process, and finishing processes. So introduction to all these processes will be given in the due course. Now that is an interesting thing, so we are going to discuss here. So to understand this abrasive jet machining process, so we have to understand this one. Suppose there is a person which is throwing balls. So first one, in the first case, he is throwing with a force of F1, and in the second case, that same person, he is throwing the same wall, okay, with a different force F2. And both the cases actually he is using same ball. Okay, so first case he is using force F1, and in the second case he is throwing a ball with force F2. Okay, so we can see from the figure, first figure, we can see that. So here this diameter of indentation into that wall is D1, and it is indenting, suppose it is indenting H1. So this is H1 here in the first case. But in the second case, when he is throwing the ball with the force F2, which is very higher than F1, so this diameter of indentation is also bigger. Also this depth of indentation in the second case also it is higher. So it is in this case it is H2. So from this figure we can see that, so H2 is this depth of indentation into that wall by the second case with force F2 is higher than the depth of indentation H1 with the force F1. Okay, so a person hits a ball twice on the wall with a force F1 and F2, and the ball makes crater of different diameter D1 in the first case, and second case with a crater diameter of D2. Okay, so in this case D2 is greater than D1 when your force F2 is greater than F1. So this diameter of depth of indentation, this H1 and H2, and diameter of indentation or crater diameter also depend on, so what is the kinetic energy? So at what kinetic energy or at what velocity that person is hitting the ball towards the wall. So in this figure we can understand or this working principle of abrasive jet machining process. So here this is the nozzle here. So this is the nozzle tip here. So through this nozzle air and abrasive particles. So you can consider air as a media. Okay, so instead of air you can consider any kind of inert gas also. Okay, so like nitrogen, argon, helium. So any kind of inactive gas or inactive gas you can consider as the base media, and abrasive particles. So these abrasive particles are actually in the micron size. So these abrasive particles, it is homogeneously mixed inside a mixing chamber. It is coming outside through this nozzle. Okay, so from here to here this is called nozzle tip distance or stand-off distance. Okay, so these abrasive particles in the base media of air, it is coming with a very high velocity. So this abrasive velocity or air velocity here around 300 meter per second or more than 300 meter per second. Okay, so these fine abrasive particles and air mixture of this, it is coming outside through this nozzle with a very high velocity. When it is impinging into that workpiece surface, it is generating a crater here. So it is generating a crater inside the workpiece surface. So here this distance from here to here, this distance is called nozzle tip distance, or we can consider this one as a stand-off distance also. Okay, so here this is a crater depth, this is the crater depth. Okay, so due to this impingement of these abrasive particles into the workpiece surface, it is generating a crater. So it is a shallow crater is generated. So this one is the crater depth here, and this is the crater diameter it is generating here. Okay, so now in this figure, so this is an exaggerated view of that crater whichever is generated into the workpiece surface. Okay, so we can see that this is a, suppose if we consider a circular nozzle, in that case a hemispherical crater will be generated, and in case of suppose if we consider a square nozzle, square cross section nozzle, so in that case that crater will be of this crater will be, so we have to mention this crater in terms of this width of this crater. Okay, and when we are using a circular cross section nozzle, in that case the hemispherical crater will be generated, so it can be represented by a diameter of this crater diameter and crater depth. So now what is the working principle of abrasive jet machining process? In abrasive jet machining process, high velocity abrasives in a media of air, it is impinging on the workpiece surface. Okay, so when it is impacting into the workpiece surface, it will make a brittle fracture, or it will generate a small crater into the workpiece surface. So these small craters, when thousands of craters are generated because of hitting of thousands of abrasive particles per second, so these thousands of small craters are generated, and after some time it will take the profile of the cross section area of this nozzle. Okay, so it will take the profile of the cross section area of the nozzle. Okay, so it will make a hole, or it will do the machining operation on the workpiece surface. Okay, so abrasive jet machining, how does it work? So jet of inert gas plus fine abrasive particles strikes the workpiece surface with a very high velocity, 300 to 500 meter per second. So because it is coming with a very high velocity because of their kinetic energy. Okay, so it stores the energy, it is in the form of kinetic energy. When these abrasive particles are touching or impacting into the workpiece surface, it will erode the surface of the workpiece surface, and because of this chipping operation, okay, so it will remove the materials in terms of small chips. So this kinetic energy can be calculated as half mv square, where m is the abrasive particle mass of individual abrasive particles, and v is the velocity of individual abrasive particles. Okay, so now kinetic energy of one abrasive particle is like this. Okay, so now thousands of abrasive particles are hitting into the workpiece surface, and it will remove the material from the workpiece surface. So what kind of operation it can do? So it can do the cutting operation, cleaning operation, polishing operation, and also deburring operation. So these are the different operations can be done by a high velocity jet of abrasive particles. So here one thing is that I want to explain. So this deburring operation is that Suppose we are doing a drilling operation. So after drilling operation, if you are making a through hole, after drilling operation, suppose this is the workpiece, you are making a hole. So this is the drilled hole. So after making the hole at the end of this workpiece, okay, so after making the hole, so you are making along this direction. So at the end, actually this kind of bars actually generated. So these bars actually has to be removed. Otherwise, this when this workpiece is assembled with another workpiece, so these bars actually will not allow to make them properly made. Okay. So also it may also damage or make a cut marks into the operator, who is doing this drilling operation or assembling operation. So before using this part for assembling with another component, these bars has to be removed. So this process is called debarring operation. This abrasive jet machining process is very good for removing this kind of bars. So it is useful for debarring operation. We can use this one as a polishing, for cutting operation, and for cleaning operation also. Okay, so for different operations we have to use different velocity of jet, because for erosive action or for making the brittle fracture we need the different kinetic energy or different velocity or different kinetic energy of these abrasive particles. So this process is very good or effective for hard and brittle material. Okay, so it is not that much effective for the ductile materials. Okay, so it is very good for hard and brittle material. So we shall discuss later how this process is very good for brittle material, why it is not good for ductile material. So this is the principle again. So fine abrasive particles, in the size of this abrasive particles is the 25 micron here. Okay, are accelerated in a gas stream of inert gas, commonly air is used. So this atmospheric pressure is at a very few times higher than the, this pressure of this jet is few times higher than the atmospheric pressure. The particles are directed towards the focus of machining less than 1 millimeter from the tip. So the stand-off distance, it is less than 1 millimeter. So in this figure it is shown, it is 0.8 millimeter. Okay. So now if we increase the stand-off distance, what will happen? So this accuracy will be reduced. Okay. So when these particles are in the gas medium or air medium, when it is coming with a very high velocity, 150 to 300 meter per second, and this radius or diameter of this nozzle. Okay, so this nozzle diameter, it is coming through a very small diameter. Okay, it is 0.3 to 0.5 millimeter, and also this nozzle tip distance or stand-up distance, it is maintained less than 1 millimeter. Okay, so when this high velocity jet is coming, so it will do the machining actions. So this particle impacts to the surface, it causes a small fracture. Okay, and gas stream carries away both the abrasive particles and also the whatever chip forms due to the fracture. So these both the things are actually carried away by the high velocity jet of air. So again, it is shown in this figure. So this is the nozzle here. So the abrasive particles from air is coming with a very high velocity. So this distance, nozzle diameter is 0.3 to 0.5 millimeter, and the stand-off distance is 1 millimeter here. Okay. So this workpiece actually, this nozzle actually, it is fixed to the machine, but this workpiece is actually attached to a CNC table. Okay. So if this workpiece is attached to a CNC table, okay, so it can be moved in X direction, it can be moved in the Y direction. Okay, so in this X and Y direction, if this table is moving, so on this table we have fixed our workpiece. So any kind of cross section can be machined by this abrasive jet machining process. Also this nozzle also can be tilted with a normal, so it can be tilted also. So by tilting this nozzle, any 3D surface also we can generate. Okay, so this abrasive particles, when it is touching to the impacting into the workpiece surface, here it is shown here. So it is making the brittle fracture from the workpiece surface, and the shape of the abrasive particle, it is, so suppose this is the tool here, this is the abrasive particle here. So this wear particle actually taken out from the workpiece surface, it is carried away with the jet of airs. So there is a flaring of jet. Flaring of jet means air abrasive particles, it is coming with a very small diameter. When it is in contact with the air, so there is a divergence of this gas. Okay, so there is a divergence of this gas. Suppose if we increase the stand-off distance here, so in that case what will happen? If we increase the stand-off distance, in that case due to this divergence of this gas, this air and abrasive particles actually it will flare. Okay, so this based on your stand-off distance, what will happen? Your diameter of this workpiece or crater diameter will also increase. Okay, so if we now increase the stand-off distance, your this crater diameter will also increase proportionally. So these abrasive particles repeatedly hit on the workpiece surface. Brittle fracture separates out the tiny particles to produce a cavity. Cavity width will be greater than the equal to the nozzle diameter. So because of this flaring action of this abrasive and air jet, so this cavity diameter or crater diameter will be greater than the diameter of the nozzle. So there are two mechanisms I told that. One is it is useful for hard and brittle material. So because of this in brittle material, these are the mechanism occurs: indentation rupture, elastic plastic deformation, critical plastic strain, radial cracking and propagation of surface energy criteria. So these are the things. During brittle erosion process, particle impact produces different types of cracks and chipping with negligible plastic deformation. So because of this brittle fracture, so and because of these operations, okay, so materials are easily removed from the brittle workpieces. But in case of ductile material, so this brittle fracture will not happen. But in case of ductile material also, there is nominal material removal rate happens, because when these abrasive particles are impacting into the workpiece surface repeatedly into a small area, so there is a strain hardening will occur. Okay, so there is a small plastic deformation into the same into that localized zone, and when many abrasive particles are impinging or impacting into the small area, there will be a more plastic deformation, and after some time there will be a strain hardening into that area. And okay, so it will become, so if there is a strain hardening of material, so after some time it will become brittle into that localized zone, and when the next abrasive particles hit into that zone, because of this it will become, it has become hard, so it will remove the material because of this brittle fracture. Okay, so this is the procedure for ductile fracture. During impact, when the yield strength of this material is locally exceeded, plastic deformation takes place in the vicinity of the impact. After multiple impacts, a plastically deformed surface layer may form near the eroded surface, and therefore the yield strength of the material increases due to the strain hardening. Upon further deformation, the yield strength at the surface of the material will eventually become equal to its fracture strength, and no further plastic deformation will occur. So at this point, material surface becomes brittle and its fragments may be removed by subsequent impacts. So now we shall discuss what are the different components of abrasive jet machining. Okay, so experimental setup of abrasive jet machining process. Okay, so now this is the schematic diagram of this process. Here you can see that, so here we need a compressor. So why we need a compressor? Because to generate the high velocity jet, we need a we need a compressed air. Okay, so for making this, for generating this compressed air, okay, so we need a compressor. So this is the compressor here, where pressure, which is multiple of, means very high pressure is generated in this compressor. Okay, so which is multiple of atmospheric pressure. Okay, so here there is a relief valve. So when this pressure is more than a certain critical value, through this relief valve, so this highly pressurized air can be removed, okay, released. So there is a drainage also is there to release the high pressure air. Okay, so now one more thing is that there is air filter or dryer. Why we need air filter dryer? Because when this compressor actually it is taking air from the atmosphere. So in that atmospheric air, there may be some moisture content may be there. Okay, so if there is some moisture content is there, so because of this moisture, when abrasive particles are mixed into that mixing chamber with that moist air, okay, so at that time what will happen, these abrasive particles will be agglomerated. When these agglomerated abrasive particles are coming through or exiting through the nozzle, at that time, because there is a very small gap, small diameter is there, it will hit the inner surface of the nozzle. Okay, when it will hit, that agglomerated particle will hit the inner surface of the nozzle, it will damage the, it will do the wear out of this nozzle. Okay, so this life of the nozzle will be reduced. Also, when this agglomerated particle coming outside and it will hit the workpiece surface, because of this lump material of abrasive particles, okay, so it will remove unevenly from the workpiece surface. So air filter and dryer is required to remove the moisture from the air. So there is a pressure gauge is there to control the pressure, air, compressed air, which is coming outside the compressor. Okay, so there is a opening valve is there and pressure regulator is there, pressure regulator to regulate the pressure which is coming from the compressor. Now there is a abrasive feeder is there. So abrasive feeder is required to feed the quantity of abrasive flow rate into the mixing chamber. So there is a mixing chamber. In that mixing chamber, so this is the mixing chamber here. In that mixing chamber, abrasive particles are coming from this abrasive feeder and compressed air is coming from this compressor. So here there is a homogeneous mixing of this abrasive particles and air is there. Okay. So now these abrasive particles are fed into this compressed air from a feeder. So this feeder may be a vibratory kind of feeder may be there. Okay. So this vibratory feeder it can be fed through a cam mechanism. Okay. Through a cam mechanism it can be, this vibration can be generated. So based on this vibration, your material this abrasive flow rate can be maintained into the compressed air. Okay, so now from this mixing chamber, when this homogeneously mixed abrasive is coming and again one pressure regulator is there to regulate the pressure of air abrasive mixture. Now after that there is a nozzle is there. So this abrasive air mix, homogeneous mixture of abrasive and air, it is coming through this nozzle here, and this is the workpiece. Ultimately it will hit the workpiece. So one interesting thing is there actually, what I told in this last slide. So because these abrasive particles, this divergence of these abrasive particles, so it is coming in contact with the air, okay, outside this nozzle. So there is a flaring of this abrasive air mixture. Okay, so there is a divergence of this abrasive workpiece mixture. So suppose we are doing a very accurate cut. In that case, to reduce the flaring action, we have to reduce the depth of this length of distance or nozzle tip distance. So we have to maintain the nozzle tip distance. In case of cutting of accurately cutting of the workpiece, okay, so we have to reduce the nozzle tip distance as less as possible. Okay, so this is the experimental setup available at IIT Kanpur. Okay, so this one here, this is the abrasive hopper. Okay, so here there is a mix, means abrasive, it is kept abrasive over here. So there is a vibrating mechanism is there. So 2 is the pressure regulator here, 2 to regulate the pressure from coming from the compressor, and 3 is the flow meter. Okay, so this is the flow meter of this compressed air, and then 4 is the mixing chamber. In this mixing chamber, this air and abrasive particles are homogeneously mixed. Then 5 is the air dryer here to reduce the moisture, to remove the moisture from the compressed air coming to the compressed air, and 6 is the RPM measuring machine, measuring instrument for vibrator inside the mixing chamber. So in that mixing chamber actually one vibrator is kept to regulate the flow rate of abrasive. Okay, 7 is the pressure gauge here again. Okay, and now this 8 is the nozzle here. So this is the nozzle. So this is the nozzle. 9 is the nozzle, and this 8 is actually it is a connecting pipe. Okay, so through this connecting pipe actually air abrasives are coming and 9 is the nozzle here, and 10 is the workpiece holder. So what are the different elements of abrasive jet machining? So first one is the gas propulsion system, second is the abrasive feeder system, third one is the machining chamber, and then fourth one is the abrasive nozzle, and fifth component of this abrasive jet machining process is abrasives. Okay, so these are the different components. So in this gas propulsion system, supply of clean and dry gas to propel the abrasive particles are carried out. So here there is a compressor or cylinder filled with gas. Here 9.5 liter per hour of gas is required. So gas should be non-toxic. Okay, so it should be non-toxic. It should not create any reactions to the workpiece. Okay, also this whoever is the operator is there, he may be in contact with this gas. Okay, so if it is toxic gas, it will may generate the health problem to the operator. So this gas should be non-toxic and it should be cheap. So because 9.5 liter per hour, this much is the requirement for this gas. Okay, so if it is not cheap, then this machining cost will be very high. So that's why generally air is used actually for this gas, and it should be easily available. So no excess spreading or diverging. So we have to consider a gas which is not spread, so that is a which does not have a diverging property. So this gas should not spread very much. Okay, so in that case inaccurate cutting will be there. Okay, taper cutting will be there. So to reduce the taper cutting, we have to choose a gas which has less spreading or diverging property. So quantity control. So this abrasive feeder, this use of this abrasive feeder is to control the quantity of abrasives into the mixing chamber by vibrating. Okay, so one cam mechanism is used. Okay, so to vibrate the abrasive feeder. So in this machining chamber, it should be well closed. Okay, so abrasive particles content should be below the harmful limit, and vacuum dust collector should be there inside that machining chamber. So because after machining, these abrasive particles may be crushed. Okay, so now dust particles may be generated. So these dust particles, if it comes to the operator, okay, so it will generate the health hazard to the operator. Okay, so that's why there should be this machining chamber should be closed, properly closed. So whatever dust particles are generated, so it should not come outside this machining chamber. Also, so there should be a vacuum dust collector to collect the whatever dust is there, it should be collected. Now agent nozzle. So nozzle is the main thing. So here high pressure gas is coming. Okay, so while exiting this nozzle, there will be high velocity gas. Okay, so inlet to this nozzle is high pressure gas. Okay, so an outlet to this nozzle is high velocity gas. Because we don't need high pressure gas, we need a high velocity gas to increase the kinetic energy. So there are different kinds of nozzles are used. So among this nozzle material, tungsten carbide and then sapphire is used. So sapphire has actually very high life. So it has 300 hours of life. So these abrasive nozzles, these air nozzles, abrasive jet machining nozzles, there are different configurations are there based on our requirement. So we can use circular cross section, or we can use a rectangular cross section, or we can use any kind of cross section to make the prototype of the workpiece to be machined, okay, into the workpiece. So nozzle pressure is generally maintained 2 to 8.5 kgf per centimeter square. So this pressure actually varies. Okay, so based on material, what kind of material we are going to machine, and what will be the material removal rate. Okay, so based on that, so what is the material removal rate, what kind of material we are machining, what kind of accuracy we need. So based on these parameters, actually we have to select the pressure, nozzle pressure. So to reduce the increased wear or stray cutting, and so because of this actually stray cutting, this whatever material is cut on the workpiece surface, okay, so it may not be accurate. Okay, so so this is due to the stray cutting. Okay, so this stray cutting can be actually controlled by using the mask. By masking actually we can control the stray cutting. So this rubber may be used, so this is less accurate, okay, and metals like stainless steel plate may be used on the workpiece surface while we don't need any machining. Suppose this is the jet is coming, so from this nozzle this jet is coming, so this is the nozzle, so this jet is coming here, so this is the workpiece surface and we need drilling and this portion. So we can put a mask over here, okay, so we can put a mask over here so that in this zone there will not be any machining although jets are impacting into that surface, okay. So by that way, so by using a mask we can control the stray cutting of the by this abrasive jet machining process. So different elements of abrasive jet machining we are discussing now. So now last element is the abrasive particles. So these abrasive particles are actually impacting into the workpiece surface. Because of this impacting of these abrasive particles, machining is going on. Okay, so there are different kinds of abrasive particles. So this is based on their actually hardness. Okay, so alumina is the soft material, soft abrasive particles. Silicon carbide is harder than this alumina. Okay, so there are other abrasive particles are there, glass beads, sodium bicarbonate, etc., boron carbide, diamonds. Okay, based on the requirement actually different kinds of abrasive particles are used. Okay, so different abrasive particles have their different hardness. So if we are using harder material, so we have to use the harder abrasive particles. So selection of these abrasive particles is entirely based on your workpiece material, and also it is based on material removal rate. Suppose if we want to get a higher material removal rate, we have to select bigger size abrasive particles and harder abrasive particles. Suppose we need a high accurate machining, so in that case we have to reduce the abrasive particle size. Okay, so by reducing the abrasive particle size we can make a accurate workpiece surface. Okay, so there are different abrasive particles, they have different applications like alumina or sodium bicarbonate. These are used actually for cleaning purpose, cutting, deburring. Mostly these are actually because they are very soft abrasive particles, mostly they are used for cleaning, cutting, deburring operations. Like silicon carbide, it is used for very harder material because its hardness is a very high, its hardness is more than alumina oxide. Glass beads, it is used for matte finish. Okay, size of these abrasive particles are like 10 to 15 micron. This is the smaller size. So these smaller size abrasive particles are used for cleaning and polishing purpose. Okay, suppose some layers or grease is there on a workpiece surface. This layer of grease or oil layer can be removed by this abrasive jet machining process. Okay, so in that case we shall use smaller size abrasive particles because in that case this kinetic energy will be less. So we need a less kinetic energy to remove the grease or oil layer from a workpiece. Large size abrasive particles are used for cutting because we have to do the brittle fracture, high brittle fracture. So we need a large size, bigger size abrasive particles. So reuse of these abrasive particles are not recommended because these abrasive particles are very cheap. So that's why it is not used. Also, when this abrasive particle is impacting into the workpiece surface, most of the abrasive particles become actually crushed. So that's why they don't have the same shape. Okay, so it becomes smaller size abrasive particles. Okay, so this whatever the sharp edge is there, it will become worn out. Okay, so these same abrasive particles are also not used. So also these tiny chips are actually generated from the workpiece surface because of brittle fracture. These chips are actually mixed with the abrasive particles and it is taken away by the high pressurized, high velocity jet. Okay, so when these chips are actually formed, these chips actually it is bigger than its shape, its size is bigger than these abrasive particles. So this is due to the formation of this chip. When if we reuse it, so this chip will clog into the abrasive into the nozzle. Okay, so if it is clogging into the nozzle, so in that case what will happen? So it will damage the nozzle. Okay, so because these nozzles are actually very costly, Okay, so that's why we don't want this nozzle to be clogged by because of this chipping action. So reuse of these abrasive particles are not recommended. Also, these abrasive particles have lower cutting ability because this it will worn out after some time. So type of work material can be machined. So already I told. So very good for brittle and fragile materials. Also, it is good for machining thin materials also because there is no direct contact of this tool to the workpiece. Only these abrasive particles are in contact with the workpiece. Also, there is no heat generation because whatever heat is generated, although it is very less, it is taken away by the high velocity jet of air. So this process is not so effective for machining of ductile materials. So carrier gas. So what are the properties of this carrier gas? It should be non-toxic, cheap and easily available. It must not flare excessively when discharged from the nozzle. So commonly used as carbon dioxide, nitrogen and air. So here one thing I have to mention that oxygen is not used as a carrier gas because it has a very high fire hazard. Okay, so that's why oxygen never used as a carrier gas in case of abrasive jet machining. So air is mostly preferred due to its universal availability and non-toxic in nature. So non-nozzle material, this nozzle also should withstand the erosive action of these abrasive particles. Because this high velocity jet of abrasives, it is also impinging or impacting into the side of the nozzle. After some time it will wear out. So this nozzle has a certain life. So it should have, this nozzle material should have high resistance to wear. It has a circular or rectangular cross section. So there are different kinds of nozzles. Nozzle materials are used. First one is the tungsten carbide and second one is the sapphire. So one interesting thing I want to show here. So this effect of feed rate. Feed rate means at what rate actually this workpiece actually moves in X or Y direction. So because this workpiece is fixed on a table, XY table, and this table is moving in X and Y direction depending on the what kind of workpiece you are making. Okay, so at what rate this table is moving in X and Y direction, that is called the feed rate. So here there are three examples are there. One is that low feed rate, because these abrasive jets are actually moving vertically. So here you can see these striation marks are there, and this table actually it is moving along this direction, in this X direction. Okay, so vertically these abrasive jets are coming and this table is actually moving in X direction. Okay, so this is the case 1. Here you can see that at low feed rate in case 1 actually the striation marks are actually very less. But when you are using high feed rate, okay, so this is the medium feed rate, this one is the high feed rate. At high feed rate we can see that these striation marks are actually prominent. So because we are moving this abrasive jet with a very high velocity, okay, so this kind of striation marks are actually generated in case of abrasive jet machining process. Now we shall discuss some models of material removal mechanism for abrasive jet machining process. So there are two models we shall discuss. So first one is the for brittle materials. So this model was actually proposed by Nima and Pandey in 1977, and it was actually published in Proceedings of International Conference. Okay, so this assumption is that material removal by normal impact only. Okay, so they have considered only normal impact by these abrasive particles. They have not considered any inclined impact, or this nozzle actually vertically normal to the workpiece, it is not inclined. Okay, so that's why material removal is by normal impact only, and abrasive particles hit the workpiece surface so abrasive particles does not hit the workpiece surface at different angles. Only at 90-degree normal angle this abrasive particle will hit into the workpiece surface. So material removal rate in kg per second, it can be given as 0.1156. This rho A, MA, then Vn square 103 sigma Fw. Okay, So here sigma Fw is the flow stress of this workpiece material. Flow stress of this workpiece material. Rho A is the abrasive particle density. M is the mass flow rate of abrasive particle. So at what rate actually these abrasive particles are mixing into the mixing chamber or into the air. So this is the mass flow rate of this abrasive particle is given as Ma. Component of particle velocity normal to the workpiece. So that is Vn is the normal velocity. Okay, component of particle velocity normal to the workpiece surface, that is the Vn here. So here from this equation we can calculate, if we know the density of these abrasive particles and then mass flow rate of this abrasive particle and normal velocity of these abrasive particles and flow stress of this workpiece material, we can easily calculate the material removal rate. So for ductile material also, Sheldon and Kanhare they proposed a model for calculating material removal rate for ductile material. So it is published in WIR in 1972. So here material removal rate it is proposed in this is millimeter cube. It should be millimeter cube. So this material removal rate is millimeter cube per second. So equal to K1 D suffix M cube, then V suffix A cube by 10 to the power 4.5 multiplied by rho A by HVW. So here K1 is the constant of proportionality, dm is the mean diameter of this abrasive grain, and then volume of impacting velocity is Va, and rho is the abrasive particle density, and HVW is the Vickers diamond pyramid hardness number of target material. So amount of material removed is related to the depth of penetration of these particles. So now we have to do the parametric analysis. What are the different parameters? First we have to find out what are the different parameters are there, and then we have to select what is the effect of parameters on process performance. Okay, so this is the fishbone diagram for this process parameters, for different process parameters in abrasive jet machining process. So here first one is the nozzle. So nozzle, if we put the nozzle, first thing will come what is the nozzle diameter. Okay. Then what is the cross section of this nozzle? Is it circular cross section or it is rectangular cross section? And then nozzle type. So this nozzle is tungsten carbide or sapphire, what kind of nozzles we are using. Second one is the abrasive. So abrasive type, size and volume fraction, flowability. So these are the different parameters for abrasives. Okay, so now third parameter is the carrier medium. So this carrier medium, type of this carrier medium, the pressure of this carrier medium. Okay, after that this fourth parameter is the mixing chamber. Mixing chamber, length of the mixing chamber, type of mixing chamber, bore diameter of this mixing chamber. Okay, then workpiece parameter is workpiece hardness, workpiece geometric details. Okay, so now machine process parameters are there. What are the parameters we can control, we can use to control the machining process? Okay, so first one is the stand-off distance, second one is the mixing ratio. Mixing ratio is the volumetric flow rate of this abrasive divided by volumetric flow rate of air. So that will give the mixing ratio. So this mixing ratio we can change by changing the volume flow rate of these abrasive particles. Okay, so second parameter is the stand-off distance or nozzle tip distance. So by changing the stand-off distance, we can change the machining condition. Okay. Third one is the traverse distance, traverse speed. At what speed actually we are moving the workpiece. Then, so another parameter is the pressure. So from this compressor actually we are generating the compressed air. So this pressure can be regulated from the compressor, or pressure regulators also there. So from there also we can regulate the pressure. So these are the input parameters for this abrasive jet machining process. So what are the output parameter? Output parameter is the machining rate. So this machining rate already we have discussed, it can be calculated as material removal rate, or it can be calculated as penetration rate. Suppose you are making a hole, so what is the volume of material is removed, that can be presented as millimeter cube per second. So that is called volumetric material removal rate. Or penetration rate means when I am making hole at certain rate, actually this distance, the depth of hole actually it is increasing. So that is called the penetration rate. Curve quality. Curve quality means when suppose you are making a blind hole or through hole. Okay. So suppose this is the workpiece, this kind of hole cross section. So after making the hole through hole, we can take a cross section of this hole. So how accurately it should be perfectly straight line. So how accurately we are making this kind of holes. So that is actually will give the curve quality. So in this case, if you see, it is not a straight line here. So this is actually curve. Inaccurate curve is generated. Curve is generated. So this curve quality actually it depends on the different machining parameters. Also, fourth output parameter is the surface roughness. So after machining, after cutting the workpiece, so we can measure the surface roughness. Or that surface roughness also will depend on the different parameters. Okay, so these are the different parameters for the abrasive jet machining process. So we shall discuss one by one of these parameters. So here typical cutting action of this abrasive jet machining. Suppose if we there are different stand-up distances there. So this distance is stand-up distance. First we shall consider this G1 is the stand-up distance. So stand-up distance we have discussed from the bottom of the nozzle up to the workpiece surface. The distance between these is actually defined as the stand-up distance. What I told that. So this stand-up distance is less than 1 millimeter. It is maintained less than 1 millimeter to reduce the flaring action. Now we can see that if we increase the stand-up, if we consider this stand-up distance as G1, which is less, okay, so in that case diameter of this crater diameter is generated as D1. Also you can see this diameter is less, but this depth of indentation is very high. Okay, so now if we increase the stand-up distance, in that case actually D2 or diameter of crater diameter also increases. Okay, for stand-up distance remain almost same. Now if we consider this G3 as the stand-up distance here, so in that case diameter of indentation or crater diameter also now increases, but here this depth of indentation, so this is the depth of indentation here, this depth of indentation slightly reduces. It is lesser than in case of this G1 as the stand-up distance. But when we are using G4 as the stand-up distance, in that case crater diameter is D4, and also in that case this depth of indentation also reduces. Okay, so if we want to make a very highly accurate cut, in that case we have to reduce the depth of stand-up distance. Okay, so effective nozzle tip distance or stand-up distance on cavity diameter. Okay, so G1 is less than G2, less than G3, and less than G4. So G3 is the less than G4. So in this case D1 is the less than D1, D2, less than D2 is the less than D3, and D3 is the less than D4. So in case of this G4 stand-up distance, this diameter of indentation is high. So this is the results shown, means reported by different researchers. Okay, so based on the stand-up distance. So this is the A. In case of the stand-up distance is 6 millimeter. You can see that the shallow one is less, the shallow hole. So although this hole is shallow, but it is not that much shallow. Okay, so now B is the actual stand-up distance is 10 millimeter. In case of C stand-up distance, in case of A stand-up distance is 2, B is 6, C is the 10, D is the 14 millimeter, E is the 16 millimeter, and F is the 20 millimeter is the stand-up distance. So here stand-up distance is high, 20 millimeter, and A case A stand-up distance is less. But from these two figures we can see from A and F, we can see that in case of this F, your diameter of indentation or crater diameter is very high because of this flaring of this abrasive jet. But in case of A, this flare or crater diameter is less. So now individual effect of individual process parameters we shall discuss one by one. So first one is the abrasive flow rate, and in y-axis we are checking the material removal rate in milligram per minute. So now if we increase the abrasive flow rate, we can see that this material removal rate also increasing, and after some time it will reach the optimum material removal rate with the increase in the abrasive flow rate. But after increasing, means after reaching that maximum abrasive flow rate, okay, so there is a stall, so it will become constant for a certain time, and if we increase the material removal rate, or sorry, abrasive flow rate beyond this optimum value here, suppose this is the optimum value of abrasive flow rate, it is around 12, okay, gram per minute. So beyond that optimum abrasive flow rate, if we increase the abrasive flow rate beyond that, you can see that this material removal rate reduces. So when you are increasing the abrasive flow rate, then more number of abrasive particles are coming out. Okay, so because of this more number of abrasive particles are there, it will, because of this more chipping action, your material removal rate will also increase. But when you are increasing the abrasive particles beyond a certain value, certain optimum value, in that case what happens? Same energy, same pressure, actually it is kinetic energy is same, pressure is constant, but we are increasing the abrasive particles. Same pressure is distributed among the same same energy is distributed among the abrasive particles. Okay. So as the more number of abrasive particles are taking part into the machining, so in that case what will happen? Individual abrasive velocity will reduce. Okay, so MRR increases only up to a certain value of abrasive flow rate, beyond which it starts decreasing here. Okay, as abrasive flow rate increases, the number of abrasive particles cutting the material also increases, thereby increasing the material removal rate. Lower abrasive flow rate leads to the lower material removal rate, to less number of less and no cutting edges. Okay, and after certain value abrasive flow rate decreases, abrasive flow velocity decreases. Okay, so if the abrasive flow velocity decreases, the kinetic energy will also reduce, and there is a reduction in material removal rate as jet pressure is distributed in more number of abrasive grades. Okay, so the effect becomes apparent with flow rate of this 14 gram per minute. So this is the critical flow rate of these abrasive particles. Okay, so now this is the effect of nozzle tip distance. Okay, so on penetration rate. So penetration rate already we have discussed. Penetration rate when you are doing the impacting by this abrasive jet machining. So penetration means this depth of indentation will increase. Okay, so with time. So this is the penetration rate. So it is millimeter per second. So what is the depth? What is the depth increase in jet with time? So that is called the penetration rate. Now, so this is the, in cutting, nozzle is positioned, just for cutting action, nozzle is positioned very close to the workpiece at 0.8 millimeter. At close nozzle tip distance, cutting rates are compromised for the sake of increased accuracy. Okay, so if we decrease the stand-up distance, if we reduce the stand-up distance, your abrasives actually they don't get that much space for generating the kinetic energy. Okay, so that's why although we are getting the high accuracy, but your material removal rate will be compromised or reduced. Okay, so close nozzle tip distance eliminates taper. Okay, so if we reduce the nozzle tip distance, this taper into the workpiece will be reduced, and also minimizes curve width. So curve, whatever the curve is generated, it will also reduce, or less shallower holes will be generated. The typical divergence angle, so because of this divergence or flaring, so this divergence angle is 7 degrees in case of abrasive jet machining. So increasing nozzle tip distance from 5 to 12.5 millimeter, abrasive jet stream is widened The stream is widened and used for cleaning. So this widened stream is used for cleaning purposes and for cleaning purposes, because they are in widened stream. This abrasive jet velocity actually reduces, so their kinetic energy is less, so it can be used for cleaning or pinning. Okay. So light duty operations such as glass frosting. So glass frosting, what is glass frosting? Glass frosting means when this abrasive jet impact into the glass material, this glass actually, although it is a transparent material, if it hit the glass material, this abrasive jet, so it will remove the surface and it will remove the surface fracture, it will generate the surface fracture into the workpiece surface, and whatever this glass surface, it will become opaque. Okay, so this opaque glass actually, these are generated for making the official cabin. Okay, so from inside actually it can you can view, but from outside actually nobody can see, although this you can use the same glass, transparent glass. Okay, so this is called glass frosting, or also you can write your name or whatever it may be by using that abrasive jet machining, okay, on a glass. So this is called glass frosting. Okay, so less velocity jet or higher stand-up distance can be used for this glass frosting operation with a nozzle tip distance of 25 to 75 millimeter. Now we can see that if we increase the nozzle tip distance or stand-up distance, this penetration rate increases. Okay, so initially this kinetic energy will increase, so that's why this penetration rate increases, and after that it will reach the optimum stand-up distance or nozzle tip distance. Okay, so after it reaches the optimum nozzle tip distance, if we increase the stand-up distance, then your penetration rate will reduce. After that, this penetration rate will reduce, because if we increase the nozzle tip distance beyond a certain value, because of this air interaction of air, okay, with the abrasive jet, okay, air abrasive jet, it interact with the outside air, okay, so it will flare out, okay, so its velocity will reduce. So after an optimal stand-up distance, its kinetic energy reduced, so that's why your penetration rate will also reduce. Okay, so at 0.75 to 1 millimeter nozzle tip distance, maximum material removal rate is achieved. Okay, low nozzle tip distance is required for higher accuracy, low curve width, and low taper angle. And higher mixing ratio, material removal rate also, if we increase the mixing ratio, in that case also, material removal rate will also increase. So if we increase the mixing ratio, your material removal rate will also increase. So nozzle pressure. So nozzle pressure has a little effect on material removal rate. So this kinetic energy removes the material. So because of this kinetic energy, this erosion takes place onto the workpiece surface. Certain minimum velocity is required. So this is called the critical velocity. So this is the critical pressure, certain minimum critical pressure is required. So why this critical pressure is required? Because you need certain pressure to generate the cutting action to take place. Okay, so it needs a certain pressure to generate the certain kinetic energy or certain velocity to generate to the abrasive particles. So that certain kinetic energy, to generate the certain kinetic energy, we need a certain pressure. So that's why at zero pressure, nozzle pressure, so this machining cannot start. So it takes, suppose in this case, it takes 10 gauge pressure. Okay, so 10 gauge pressure to generate the cutting to takes place. Okay, so kinetic energy removes the material by erosive action. Certain minimum velocity for the given material is required for cutting action. For machining glass, 150 millimeter per second using silicon carbide of 25 micron abrasive are used. Okay, so this is the effect of stand-up distance again with the volumetric material removal rate. Now we can see here, if we increase the mixing ratio, so what is the mixing ratio is volumetric flow rate of abrasive particle by volumetric flow rate of air. Okay, so volumetric flow rate of abrasive particle and with the volumetric flow rate of air. If we increase the mixing ratio, okay, by increase the mixing ratio, your material removal rate will also increase. Okay, so standard, if you increase the standard distance, it will increase, metal level rate will increase, and after that it will reach an optimum value, after that it will reduce. Okay, now if you increase the mixing ratio, means more abrasive particles are mixing into the chamber, okay, your metal removal rate will also increase. So this volume flow rate of abrasive particle by volume flow rate of carrier gas will give the mixing ratio. Maximum is observed for a certain means between for a certain m. Maximum metal removal rate is observed, and instead of mixing ratio we can calculate the mass ratio also. So mass ratio is volume flow rate of this abrasive by volume flow rate of abrasive plus carrier gas. So how to calculate this metal removal rate? Okay, so it is volumetric metal removal rate. It is can be calculated as Q. You can see there is a function of theta. So theta is the impingement angle. So earlier we have considered the vertical nozzle. So this nozzle can be inclined with the vertical axis. Okay, so that will give the impingement angle. And m is the mass of the impacting particle. V is the velocity of this impacting particle, and sigma is the flow stress of this workpiece material, and N and C is the constant here. Okay, process capabilities. So process capabilities, it has a very less metal removal rate, 15 millimeter cube per minute. So low metal removal rate. So intricate details in hard and brittle materials. It can generate intricate details on hard and brittle materials because abrasive particles did not touch. Work tool does not touch the workpiece surface like in conventional cutting or milling operation where tool directly touch the workpiece surface. So here abrasive particles which is in the micron range, submicron range, these abrasive particles are touching to the workpiece surface. And also this nozzle diameter is also very less, 0.3 to 0.5 millimeter. So intricate details can be generated on hard and brittle materials. So narrow slots also can be generated, 0.1 to 0.25 millimeter. These kind of slots are generated. Tolerances obtained on this abrasive jet machine surfaces plus minus 0.12 millimeter, and minimization of taper can be done by properly setting angle of nozzle with respect to the workpiece. And then thin section, brittle material, inaccessible areas. So inaccessible areas also can be cut by this abrasive jet machining. Almost no surface damage, okay, no heat affected zone, because whatever heat is generated, minimum heat is generated, that is carried away by the flowing of air. So that's why very less heat affected zone is generated. And it can generate very good surface finish, 0.25 to 1.25 micron surface finish can be generated. So minimum radius that can be produced is 0.2 millimeter in case of abrasive jet machining. Steels up to 1.5 millimeter, glass up to 6.3 millimeter thick is possible to cut by the abrasive jet machining process. And if no taper can be tolerated on the cut edge, the nozzle or the workpiece can sometimes be tilted to component compensate. This has the effect of negative taper or the part or on the part and doubling the taper on the square. So these are the applications for abrasive jet machining process. So these are the components, indicate components you can see. So these are the components are generated. These are the components are actually generated on using abrasive jet machining process. Okay, so these are the components are generated on abrasive jet machining process. Okay, so these applications, these are the small components, intricate components are generated on aluminum sheet. So these are the applications: manufacture of electronic devices including fragile components, deburring of plastics, nylon, Teflon parts, glass frosting already I told for making the opaque glass, this glass frosting, deflushing of small castings. So after casting you can see small bars, small protrusions are actually left after casting operation. So that can be removed by deflushing operation. So that can be done by this abrasive jet machining process with very high depth of or stand-up distance, using a very high stand-up distance, also using low pressure. Okay, so this deflashing of small casting, removing of flash and parting lines from the injection mold parts, deburring and polishing of plastic, nylon and Teflon components, cleaning of metallic mold cavities which otherwise may be inaccessible. So inaccessible mold cavities can be polished by this abrasive jet machining process. Cutting of the section fragile components made of glass, ceramics, removing of the glue and paint or cleaning of this glue and paint from the paintings and leather objects can be done by abrasive jet machining process. Frosting of interior surface using glass tubes, permanent marking or rubber stencils, okay, can be done by this abrasive jet machining. On a rubber workpiece, you can make a permanent marking, or you can write something on a rubber workpiece by using the abrasive jet machine. Using less pressure, drilling on glass wafer, cutting of titanium foils, cutting, making, engraving, cutting thin section workpiece can be done by this abrasive jet machining process. So different abrasive particles have different applications. Okay, like if we consider aluminum oxide as an abrasive particles with grain size of 10 micron, 20 micron and 50 micron. So these are used for cutting and grooving operation. Silicon carbide, which is harder than the abrasive aluminum oxide abrasive particles with a 25 to 40 micron, is also can be used for cutting and grooving operation. Sodium bicarbonate, its diameter is 27 micron. So it is used for light finishing below 50 degrees centigrade temperature. Then dolomite also is used with 200 Ms. It is used for etching and polishing purpose. Glass beads of 0.635 to 1.27 micron are used for light polishing and fine deburring operations. So these are the different nozzle materials. This is the tungsten carbide and sapphire. Tungsten carbide, it has a life of 12 to 30 hours, and it is a round tip. It is 2.2 to 1 millimeter, or rectangular tip 0.7 to 0.5 to 0.15 cross 0.25. So this is the dimension of this tip, rectangular tip. So it has a life of 12 to 30 hours. But in case of sapphire, its life is 300 hours. Okay, so sapphires mostly generally is used with round cross section with 0.2 to 0.8 millimeter diameter. So there are some advantages and disadvantages of this process. Advantages are machine is heat sensitive. So heat does not means heat is not generated. Whatever heat is generated, it is taken away by the carrier gas. Very little and no heat generation to non-contact cutting and microscopic material removal. Very small material removal is there. Low capital investment. So in only that consumable is that actually this nozzle. So nozzle is costly. Other than other things, other components of this abrasive jet machinings are not that much costly. So that's why capital investment is less. No part chatter or vibration like in conventional machine process, their vibration or chatter marks are generated. So that kind of things are not there in the abrasive jet machining. Machines, very hard materials. So very hard materials can be machined. What are the different disadvantages? Applications are restricted to only brittle material. So it is not suitable for machining ductile material. So for ductile material, this material removal rate will be very less. Sometimes additional cleaning operation is required to machine the part, as particles can embed into the workpiece surface. And stray cutting and machining accuracy is poor, so that's why because of the stray cutting, taper cut is generated. Nozzle wear rate is very high because abrasives are actually passing through the nozzle. So wear rate of these nozzles are very high. The process tends to pollute the environment because these particles are coming with a very high velocity. In the mixing chamber, it is not properly cleaned, it is not properly locked. These abrasive particles, glass abrasive particles will come outside, and also it has a very low material removal rate. There are few applications you can see using this abrasive jet nozzle, these kind of complicated details. You can generate into the, so these complicated details also you can generate into the workpiece. So this kind of complicated details can be generated into the workpiece. So here is the example of abrasive jet machining. So this kind of design can be generated on a eggshell. Okay, so on an eggshell actually this kind of design is generated. So now we shall discuss some solved example and we shall discuss some question bank. Now here it is shown that diameter of a nozzle in a certain abrasive jet machining process, the nozzle diameter is considered as 0.9 millimeter, although it is in 0.3 to 5 millimeter nozzle diameter, but here it is considered 0.9 millimeter diameter nozzle is used. The exiting gas jet velocity is 300 meter per second. The mixing ratio is 0.3. So mixing ratio is volumetric flow rate of abrasive by volumetric flow rate of this carrier gas. So that is 0.3. So now we have to calculate what is the volumetric flow rate of carrier gas and what is the volumetric flow rate of abrasive particles used. So now total volume of flow rate, volume flow rate can be calculated is pi by 4 d square into velocity of this abrasive jet. Okay, abrasive air abrasive jet is will give the total volume flow rate. So volume flow rate, it is a summation of total volume flow rate is a summation of abrasive, and here is the volume flow rate of this carrier gas. So this volumetric flow rate is pi by 4, 3.14 by 4. D is the 0.9 millimeter is the nozzle diameter, and then velocity is 300 meter per second. So 300 into 10 to the power 3, it will give millimeter cube per second. Okay. Now mixing ratio is told VA volumetric flow rate of abrasive by volumetric flow rate of VR of carrier gas is given as already given as 0.3 millimeter. 0.3. Okay, now total volume flow rate from this equation can be calculated. It is calculated as 190 into 10 to the power 3. So now if we take from this equation, if we take VR as a common, so VR equal VR multiplication of VA by VR plus 1. Okay. So here if we multiply this VR with this second term, so it will give VA plus VR, which is equal to 190 by 10 to the 190 into 10 to the 10 to the 3. Now if we take the VR as a common, okay, it will be VA by VR, which is 0.3 plus 1 into VR will give the 190 to 10 to the 3 millimeter cube per second. So from this equation we can calculate this VR as 146.734 into 10 to the 3 millimeter per second. Now VA plus VR equal to 190 into 10 to the 3. So if we know the VR, then we can easily calculate the VA also, volumetric flow rate of abrasive. So it is asked here. Question: can we use abrasive jet machine process for metallic as well as non-metallic workpiece? Yes. So it can be used for metallic and non-metallic, but this workpiece should be strong and hard materials. So workpiece should be very hard. Can we use oxygen as the carrier gas? So it cannot be used because of this fire hazard. Can we get uniform diameter hole drilled by agent process in glass? No, because of this, as the nozzle tip diameter keeps increasing, the jet dimension, the jet strength actually keeps decreasing and flaring keeps increasing. So that's why we cannot use nozzle tip distance. We cannot get the same workpiece, okay, by increasing the nozzle tip distance. So these are the question banks, different question banks for this abrasive jet machining process. Okay, thank you.